Okay, let's get started. We got a lot going on today and next week, so let's spend some time talking about logistics first. Let's start with today. You have your third report due tonight. Given the CS Fair and everything else that's going on, there will be no quiz tonight, so one less thing to do. Sound fair? Okay, so that's the third report. We're going to spend some time talking about the final project now. And again, just as a reminder, we're here next Friday for our exam period. And as we discussed last time, we will finish exactly at 1:15 p.m. So back to today, we'll talk about the final project. And we will finish off the last slides in lecture 27. So we're going to kind of combine our discussion of sideboard technology and BCI all into the one lecture. There is no lecture 28. Okay, CS Fair this afternoon. Who's presenting a project? Okay, I see some of you have the T-shirts. What do the binary digits say? Not quite. There's a hint. What's that? Oh, Gretchen, good job. Okay. I don't know if the error is from you, but there is, I think, something that's missing, right? There's 7 digits instead of 8 in one of the block of 8. Okay, I'll leave that as a homework assignment for the CS Fair. Okay, so do make an attempt to try and see as many projects this afternoon. I think we have somewhere around 160, so should be quite interesting. Okay, let's see. Am I forgetting anything? I don't think so. All right, let's talk about the final project. Most important thing right up at the top, next Friday, please bring your Leap Motion device back. I know some of you will be here again in the spring semester, but we found that if we don't collect them right at the end of the semester, often we don't see our Leap Motions anymore. So please do remember to bring them to class. If we don't get your Leap Motion back or you don't give us a good reason for why it's lost, no final grade for the final project. Sound fair? All right, don't forget. Okay, so what are you actually going to be doing for the final project? There are 3 pieces. You're going to be submitting a 3-page written report. You're going to be submitting a 4-minute YouTube video. And the third part is going to be talking over your 4-minute YouTube video during the exam period. Those 3 pieces. So the written report is worth 4% of your grade. The video itself is worth 3%, and your oral presentation 4%, which, given my fried brain on the last day of classes, I think sums to 11%, right? Okay. All right, 4, 3, and 4. Okay. Very, very important. You're going to be submitting the written report as a PDF and a link to your YouTube video to Blackboard by 11:59 p.m. next Thursday. You need to get it in by 11:59. There will be no late extension. So if you do not submit anything by that time, you get 0 for the written report and the video. The reason why is we need to stitch together all 33 of these videos in a playlist and make sure everything's working for 10:30 the following morning, so we can't stitch in any late submissions. We are not going to be switching the laptop during the exam period, so even if you come to class with a video that's late, but you have it and ready to present Friday morning, we can't do it. We don't have time to switch computers. All right? So no late penalty on this one. Okay, so let's talk a little bit about what exactly you will be doing. You're going to be adding in a little bit of new functionality to your system. I thought about having you do a second round of user testing, but given the fact that everyone's doing exams and everything next week, I think it might be a little bit more chaotic to do another round of user testing. Better, I think, to try and add in some new functionality to your system. I've given you some examples of things you might add, but you can also come up with your own. If you do come up with your own, read through the examples that I have here to give you an estimate of sort of the amount of new functionality we're looking for. Assuming your system is working and relatively modular, you should be able to add in some new functionality with relatively little change to your existing code base. All right? Okay, so here's some examples of things you might be able to add in. The first one is sort of an advanced lesson. So assuming your user has used your system and learned all 10 digits, now you flash up on the screen 3, 1, and they need to sign 3 and 1. And while they're doing that, your KNN learner is not telling them whether they're getting it correct. It's only going to tell them at the end whether they got the whole sequence correct or not. Assuming they get the sequence right, now the user will be shown a triplet of digits, a longer sequence. If they get that longer sequence right, they're shown 4 digits. If they get it wrong, they go back to 2 digits. So basically allowing them to reinforce and really memorize these digits, right? That they're right there and ready to go. Okay, that's one example. You might also want to try and add in some letters in addition to digits. So obviously, if you're going to add in some letters, you need to go back, re-record using, I don't remember which deliverable, but whatever deliverable it was, record some letters, add it to your training set, retrain the KNN learner, and away you go. Again, assuming everything is relatively modular, that shouldn't take too much work to do. Number 5 is a little bit more challenging. This would be expanding your KNN learner to recognize digits that change over time. So J is this. So you remember, if you remember back, one static gesture is 30 numbers. If you were to capture something that's happening over time, it's going to be 30 times K, which is however many frames you capture during a gesture. That one's a little bit more challenging, but you're welcome to attempt it. Number 6. This is a project that's been attempted in the past, which I think is a good one. This really helps with, again, memorization. So instead of showing the actual digit you want, you show a simple algebraic equation, 3 plus 4, and the user should sign the answer to that. Again, pretty straightforward. Some of you have already started to do this, I think, but you could take this a little bit further and gamify your system. So again, maybe practicing ASL digits over and over becomes a little bit old after a while. How can you make this a little bit more interesting for your user? Okay, those are just some ideas you can attempt. You can also come up with an idea of your own. Sound good? Okay, so the written report then, again, is a 3-page write-up. The first page is describe the functionality that you're going to add. You might describe sort of some use cases. So how is the interaction actually going to play out when the user encounters this new functionality? And then the second page is describing how you needed to change your code to do so. Okay. And then the final page, I want you to sort of think about what would happen if you had another semester and you could recruit, I gave you enough money to recruit 100 users to test your system. What kinds of users might you want to recruit? So how would you actually do this, right? You've probably got some experience now that different kinds of users might use your system in different ways. Who might you recruit? If you had enough money and you were able to record more information from your users as they were interacting with the system, what might you record? So what we're looking for on this final page here is that you're demonstrating that you've sort of absorbed a lot of the concepts about user testing in this course, and assuming you had the time and the financial and the human resources to do so, how would you really figure out where the weak points in your system actually are? Make sense? Okay, should be pretty straightforward. And then a 4-minute video, not that different from what you've done before, but a few additions. So 4 minutes is not a lot of time. The first minute might just actually be a single slide with some bullet points on it. Again, summarizing the functionality that you added to your system. And I'm sorry, it doesn't say here, but you might also want to describe the changes you need to make to your code. So I'll add that to point number 2 here. So a single slide, what you changed and how you needed to change your code. Minute 2 and minute 3 might be a video of you exercising the new functionality that you added to your system. And then the fourth and final minute is again a second slide summarizing your ideas about how you would expand user testing given another semester to do so. Okay, capture that all in a silent 4-minute video and upload it to Blackboard by next Thursday night. So far, so good? Okay. Okay, so then what's going to happen on Thursday and Friday? So again, Friday morning we will take all of the videos and we will stitch them together into 33 videos. I will embed at the hour mark and the 2-hour mark a 15-minute break. And assuming we get 33 4-minute videos with 2 15-minute breaks, that gives us a YouTube playlist that runs for exactly 165 minutes. And it'll get us out of here at exactly 1:15. The unspoken part of this is that the playlist will never pause. So when one person finishes and you see your video come up, you come to the front of the room and present your project. Okay, I haven't posted the presentation schedule. In past years, I submitted it early and people kind of showed up when they were presenting, so I'd like you to all be here. I will bring lots of coffee and donuts, so it'll be like a little mini conference. So please be here to support your fellow presenters, even if you don't present until later in the schedule. So when you come in next Friday, 10:30, I will have the schedule written up here at the front. Okay, so again, we'll start the playlist right at 10:30. When your presentation starts, you'll come up here and you'll get your silent bullet points, talk over them, talk over the video where you're demonstrating the functionality and your ideas for future user testing. Okay. If you haven't done this before, some of you have taken my robotics class. This is kind of a novel way to present. I suggest you practice, practice, practice. It's only 4 minutes, so you can practice a few times. If you run over, unfortunately, I'm going to have to close you down and invite the next person to come up, right? So you really want to make sure your timing is quite tight for this 4-minute presentation. The video itself, obviously, that you submit should be exactly 4 minutes. If it's too much over and if it's too long, we're going to have to deduct a few points for that one. Okay, I think that's it. Does that make sense? Any questions about the final project? Yes? If it's 3:55, that's fine. You don't need to add filler. We'll end a little bit earlier. Okay. 4:05, I might have a problem with that. Fair enough? Okay. Okay, that's the final project, so good luck. If you have any questions, email me, and if it's something relevant to the whole class, I'll post an announcement to Blackboard, because obviously we won't see each other until next Friday. And free coffee and donuts on Friday. Okay. Okay, so let's finish off the material for the course. Again, looking inward, we're now looking at technologies that insinuate themselves literally into the sensor motor feedback loop that our human user has with the environment. So last time we took the human brain and we broke it into a number of components. So before we jump back into lecture 27, I'm going to further unpack our sensor motor pathways, because some of the technologies we're going to look at today interfere with that pathway at different points. So as always, we have our environment out here, and we have our muscles, which are influencing the environment in some way, and then our sense organs are capturing the repercussions of that action. So we're going to focus mainly on eyes and ears today. Okay, so muscles cause an action on the environment. Ears capture pressure waves as sensation, and eyes capture photons as sensation. In the case of your eyes, the signal is passed on to your retina at the back of your eyes. Once your retina captures a signal, it's passed on to the optic nerve. And the optic nerve is some wiring that goes from your eyes at the front of your skull all the way to the back of your skull. And at the very back of your brain is the visual cortex, which is that part of the brain that's responsible for interpreting the visual scene in front of you. And from there, signals go to all sorts of places. But I'm just going to summarize this as CNS, which is the central nervous system. One of the main jobs of the CNS is to combine information that's coming from lots of different sense organs. Also executive control, so if you internally decide to do something, and then obviously this is passed back out to the motor cortex. And the motor cortex is primarily a strip of your brain right across the top of your head here. And this is where you think about the action that you're about to perform. You think about what you want to do, you pass that signal on to the muscles, and you actually do it. We looked at cochlear implants last time. So let's skip ahead to cochlear implants. So after the eardrum, a signal is passed on to the cochlea. From the cochlea, like in the visual system, the signal is passed on to the auditory cortex. We're going to skip over some of the intermediate steps here. Auditory cortex, which is obviously the part of the brain responsible for interpreting auditory signals onto the CNS, and around we go, right? So we have this overall feedback loop. So in the case of the cochlear implants, we're assuming that something about the cochlea is damaged, so we have some technology, some interactive technology here, which is taking pressure waves and capturing them with the little microphone that's just by the ear and sending that signal either into the cochlea or just beyond the cochlea, right? We're trying to bypass the eardrum and the damaged cochlea and send the signal right on to the auditory cortex. We ended last time by looking at a different approach, which isn't strictly a cyborg technology. Again, this is for someone who cannot see or cannot hear, where we're trying to capture a signal that is meant for, in this case, the eyes. So the cameras in the glasses here are capturing a visual scene and changing it into an auditory signal that is passed to the ears, which in this project is known as a soundscape. And I won't play this for you again, but the idea here is the brain, through the auditory cortex, gradually learns to interpret a sound as something that is seen. So far, so good? Okay, so let's keep going. Let's switch now again to, or let's stay with the visual stream here. So what happens if some aspect of the eye is damaged and the retina is damaged? There is work being done now on retinal prostheses or retinal implants. Most of this work is still in development. However, in the United Kingdom, there was the first bionic eye or retinal implant surgery carried out back in 2015. So what happens in this case? Well, the retina, as you can see in this little cartoon here, sits at the very back of your eye. Again, we have a blind subject who is wearing glasses where there are cameras looking in the direction that the eyes normally would, capturing a visual scene and supplying it to an electrode array, which is sitting where the retina normally would. Initial work on this was done with a 5x5 resolution, so obviously very, very low resolution. Some research teams were working on a 25x25 array back in 2010. I'm not sure about the actual implant that was performed back in 2015, but it's giving some signal, supplying some signal past the damaged retina to the optic nerve. Actually, I think we have a little bit of time, so let's actually play this video if I can.
This is what the world looks like to Ray Flynn. His central site. This is what the world looks like to Ray Flynn. His central sight is gone and he relies entirely on his peripheral vision. Ray told me it severely limits what he can do. Hi, Ray.
I can't use the cash machines. I'd like to be able to go shopping and finding things and doing my own PIN number in the bill, but my brother has to do all that. He does everything.
I'm going to look at the back of your eye.
Ray has dry, age-related macular degeneration, AMD, which affects mainly the elderly and happens when cells in part of the retina become damaged. A few hours later, the surgical team at Manchester Royal Eye Hospital are ready to wrap this, the retinal implant, around the back of Ray's right eye, a world first for his condition. Age-related macular degeneration is the most common cause of sight loss in the developed world. At least 500,000 people in the UK are affected, so there is vast potential for any technology which can improve visual function and enhance quality of life. This is how it works. The patient wears special glasses which have a built-in video camera. The visual information is wirelessly transmitted to the retinal implant on the eye. Electrodes stimulate the retina's remaining cells to send those visual signals to the brain to interpret. 2 weeks after surgery, the key moment as the bionic eye is switched on.
So please close your eyes.
Ray is asked to keep his eyes closed during the test so the team can be sure whatever he sees must come from the implant relaying information from the camera on his glasses.
Diagonal.
Success.
Vertical. Horizontal. Oh, it was wonderful with my eyes closed to see the bars on there. It was really good.
For his surgeon, it's highly significant.
This provides hope to patients with not only this condition, but also to other patients with loss of central vision due to degenerative diseases. So this is just the beginning, and this could be the beginning of a new era.
Implants can't deliver fine visual detail like a human eye, but the technology is improving, and trials like this are crucial to the development of bionic sight. Fergus Walsh, BBC News, Manchester.
Okay, so still relatively low resolution, getting to the point where it's just a matter of increasing resolution. What exactly does Ray see in this case? He was able to correctly identify these beams, but what do you imagine he's actually seeing?
Contrast?
It's probably something like that, right? Something that's very obvious, right? So these high contrast lines, that's relatively straightforward. He said he'd like to look at an ATM machine and be able to type in digits, maybe not quite yet, but on the way there, right? Okay, so there's hope for users in which it's the downstream part of the visual sense, right? So aspects of the brain that are working upstream can still interpret signals that are coming now not from the retina but from this electrode array. Yes?
Is it possible to quantify what resolution you're seeing in, or is it not really on that scale?
It's tricky, right? Because when you ask Ray what he sees, well, in this case they weren't asking. Well, they were asking what he sees, horizontal, vertical, and so on. He's reporting what his optic nerve is reporting to the visual cortex, right? And like we've seen in all the cyborg technology we've looked at so far, that technology is probably providing something quite different from what the retina does, even if in future versions they're able to greatly ramp up the visual resolution. Right? Whatever the retina is doing is not actually taking a 640 by 480 pixel array and providing it to the optic nerve. There's some transformations that occur at the retina as well. Okay. Okay. Here's a similar example. In this case, however, this is, again, a relatively older project, but pretty interesting here. So in this case, the interactive technology is directly stimulating the visual cortex. So in this particular, on these two subjects that I'm going to show you in a moment, it is actually the optic nerve that is damaged. So now we are going I'm sorry, we're going more upstream. We're bypassing all three of these downstream elements of the visual stream and providing an electrical signal directly to the visual cortex. But what happens when you start to interfere with the sensory motor system further upstream, closer to the central nervous system? So in most of the subjects that have had this implant done, they report seeing phosphenes. So if you close your eyes and you see those sort of bright little blobs that are moving around on the inside of your eyelids, that's what subjects tend to report seeing. So the tricky thing, though, is if the subject is looking at a scene and there happens to be a bright object in the upper right part of their visual field, they may see a phosphene that's in the lower left part of their visual field. So there isn't, clearly it's much more difficult to maintain a one-to-one correspondence between spatial arrangement in the photons that are actually falling on the camera and what the visual cortex reports to the central nervous system. Right? So in this case then, we need to do some machine learning where if we supply a bright light in the upper right part of the subject's field of view and they report seeing a phosphene in the bottom left, alter whatever signal processing is going on in the interactive technology until what? Until it gets it right, right? So until the subject reports seeing a phosphine in the bottom, the top right, right? Now we do that. Now we add a different training instance where we might shine a light into the lower left part of their visual field. They report seeing a phosphene somewhere else. We keep tuning the interactive technology until they see a phosphene in the appropriate part of their mental image. Yes, Kelly?
Would you say the biggest hindrance is, I mean, cochlear implants obviously is something that's been around for a while. Do you think it's mainly because that kind of bypasses a more mechanical part, and whereas talking about actually replacing eyesight, it's just directly to the brain?
So, right, is it more, for these different sensory channels, is it a more or less direct connection to the brain? They're all indirect, right? The photons that are falling here, or the pressure waves that are falling here, are completely different from whatever neural pattern is being provided to the central nervous system, which is the part of the brain that's trying to make sense of what you see. This is where things get sort of tricky, right? It's what sort of sense your brain makes of these patterns which are arriving downstream.
So is it just more difficult to make sense of those patterns when they're visual as opposed to auditory?
It's more difficult when you're trying to supply the signal further upstream, right? Because there's a lot of intermediate processing that is going on in the downstream parts of the visual system and the auditory system. The more of these you bypass, there are more intermediate computations which we don't know is what's really going on there, right? All of these components of the visual and auditory system are not well understood. So we don't actually know what transformations are going on. So it's harder to know what actual transformation we should provide if we're supplying a signal further upstream. It's not so much which modality we're dealing with, it's how upstream we're trying to go. Right? Okay. Okay, so here I'm going to show you an example. I apologize, the quality of the video isn't very good, but this was an attempt to try and show what a subject sees, quote unquote sees, when we're bypassing eyes, retina, and optic nerve.
Something right here. Right here.
That's not going to work. Hold on a second.
Something right here. Right here. Right there. Okay. And right in front of me. Right in front of me. Now I passed him. Oop, now I got him. Now I got the blind. Okay, back to the blind. Little break. And the mannequin. Right here.
So for this particular subject, as you could see in the initial visualization here, they reported that they saw these sort of light and dark dots on the inside of their eyelids. That's what the visual cortex seemed to be supplying to the CNS. If you did this with a different subject, they would see something completely different. Okay. Okay, as amazing as that is, this is subject number 2.
I was able to very carefully drive and look from my left side to my right side, making sure I was between the row of trees on the right and the building on the left. When I got near any obstruction in the front, I would see that there was an obstruction. I would also see the lack of obstructions, and then when I backed up, I would be able to inspect for obstructions there. It was really a nice feeling.
Okay, pretty impressive. I don't know if we're actually going to allow people with these technologies to drive, but the words they were using, right? I see an obstruction, I sort of know where to park, that sort of thing. It's hard to see here. This subject reported initially seeing something that looked like a dot matrix. So a bunch of dots that weren't actually moving, but again were sort of darkening and lightening. And over time, their brain adapted to interpret that pattern of light and dark dots as obstructions or free to drive or what have you. Okay. Okay, so that's creating interactive technology that bypasses part of the incoming sensory stream. What about going the other way? So if we're dealing with people that are paraplegic or quadriplegic, they cannot control some or all of their muscles, can we embed some technology in this case, the motor cortex, grabbing signals from the motor cortex, supplying them to a computer. Sorry, I had the arrow the wrong way here. Supplying them to a computer that is supplying some action to the user's external environment. So think about an action, and that action actually occurs. There's a switch here between slide 12 and 13 if you have a copy of the slides. Let's have a look at how this actually works first.
Study participants will undergo a surgical procedure where a small sensor is placed on the area of the brain responsible for movement. This sensor is connected to a pedestal that is attached to the skull and protrudes through the skin. The sensor records electrical signals from the brain, and these signals are fed into a device where they are interpreted by an operator using special software. From there, the signals are fed to a computer through which a study participant will attempt to control a cursor on a computer screen. The goal of the study is to evaluate the quality, type, and usefulness of cursor control that participants can achieve by using their thoughts.
Okay, so in this case we now have an electrode array which is not supplying signals to the brain but capturing signals from the motor cortex, which is the part of the brain responsible for motor imagery. So thinking about doing something. So if you put your hand out in front of you and you move your arm left and right, a split second before your hand actually moves, there are certain signals in the brain where you thought about that action and then carried it out. Similarly, you can choose not to move your right hand, but think about extending your right hand out in front of you, and then think about moving your hand to the left or the right. If you do that, the signal is a little bit weaker, but that signal is very similar to the signal that's produced when you actually move your hand to the left or the right. If a subject is placed, again, this is obviously a cartoon, this hasn't actually been carried out yet, but if this were to actually be conducted and the subject were to be asked to move the cursor, what motor imagery would the subject be imagining?
I mean, you could set it up to anything, but I imagine something like this would be the physical movement of a mouse.
The physical movement of a mouse, right? So again, HCI, it depends on who we're dealing with. So if this is someone who in the past had the ability to move and has a physical experience with moving a mouse, that's probably what they imagine if they had subsequently lost the ability to move their arms and now were asked to move the cursor. They would mentally imagine reaching out with their dominant hand, which is most of the time their right hand, and clicking with their index finger and dragging left and right or forward and back. What about someone who is born without the ability to use their arms? If you ask them to move the cursor, what are they thinking about?
I'm thinking they would just, in a sense, visualize the cursor in different spots.
Okay. So that's relying on the visual cortex, right? So what it's like to actually see a cursor move, which is very different from imagining reaching out to a mouse or reaching out to a touch screen and trying to move a cursor yourself.
That's true, because this thing focuses on movement aspects.
Movement aspects. If you've never actually moved before, right, could be, right? So there are two very different groups here that you're going to have to come up with two very different systems for. So if this is for someone who was born without the ability to move, they may still have the motor strip, but it may not be very well developed. There are parts of the motor strip that are responsible for moving internal organs, so actually digesting and excreting. Perhaps you could actually tap into those aspects of the motor cortex. The part of the motor cortex responsible for reaching and clicking and moving probably isn't going to do much for you for a subject that has never actually held a cursor in his or her hand before. So this aspect of human diversity becomes really important when we're talking about cybernetic implants for people that had the ability to see and lost it, or had the ability to move and lost it, compared to those who could never see in the first place or were never able to move since birth. Very, very different. Okay. Again, given this cartoon, assuming, let's imagine the easier case now where we have someone who actually did have the ability to move before, and they're placed in this training environment. What do you think this training environment is actually doing?
Imagine it's like learning how their signal responds, and are they able to give feedback upon whether it's working or not?
Absolutely, right? There has to be a feedback loop here. There has to be some machine learning in the loop. We all have a motor strip, but like your thumbprints, they're all different. So if we have two separate subjects and we ask both of them to imagine reaching out their right arm, grasping a mouse, clicking and pulling, you would get two very different signals from those two different subjects. And we're going to have to train this system on each subject to interpret that subject's motor imagery to associate with move right, move left, click, and so on.
So the drones that are controlled by EEGs, I'm sure you've seen them before. Maybe the next slide or something.
You mean these drones?
Yeah.
Okay.
I'm just curious. So does that mean that each time that machine learning algorithm needs to be trained to that individual person, or
Absolutely.
Can you just can't put it on?
You just can't put it on, right? So again, here's another example. So instead of moving a cursor in 2 dimensions, which is easier, again, assuming someone actually physically manipulated a mouse because you kind of know where to go looking. In this case, we're asking the subject to use their hand, and again, in the figure caption here, it says, bioelectric signal generated from motor imaginations of the hand. So they're wearing an EEG cap, which captures electrical signals from the surface of the brain, which works well for the motor strip, which happens to be on the surface of the brain. And we're looking for motor imagery from the hand. So if you were asked to control the drone by imagining movements of the hand, what movements would you imagine to control the drone? What specific hand movements?
Like keeping it flat.
Okay, right, so you might actually move the X, Y, and Z coordinate of the hand. This means move the drone left, move the drone right, move the drone back, move the drone forward, down, and up. Is that the only solution? Exactly, right? We might have to be very specific in the instructions. Maybe this is forward, this is back, this is left, this is right, up, down. That's also motor imagery of the hand. Without specific instructions, different users might imagine moving the drone in different ways, which exacerbates the difficulty of our machine learning task. So we might, for example, if we were developing a test harness for this technology, we might show the user a video of hand movements, right? I want you to imagine as best you can this actual hand movement for left. Not this hand movement, not this hand movement, this hand movement. We might have to be very specific. Okay. Okay. So that's, again, technologies which are somehow interfering with a sensory stream or a motor stream. What happens if we connect our interactive technology directly into the central nervous system? So bypassing sensation and action altogether. This one becomes increasingly difficult to think about, but this is sort of the extreme end now of brain-computer interaction. You're going to think about arbitrary things, not necessarily imagining movement of your body. And can we train some interactive technology to interpret your thoughts appropriately? Okay, so there's some work on this already. We're going to, I guess, finish with this TED Talk today by Tan Lee of Emotive Systems.
Up until now, our communication with machines has always been limited to conscious and direct forms. Whether it's something simple like turning on the lights with a switch, or even as complex as programming robotics, we have always had to give a command to a machine, or even a series of commands in order for it to do something for us. Communication between people, on the other hand, is far more complex and a lot more interesting because we take into account so much more than what is explicitly expressed. We observe facial expressions, body language, and we can intuit feelings and emotions from our dialogue with one another. This actually forms a large part of our decision-making process. Our vision is to introduce this whole new realm of human interaction into human-computer interaction, so that computers can understand not only what you direct it to do, but it can also respond to your facial expressions and emotional experiences. And what better way to do this than by interpreting the signals naturally produced by our brain, our Center for Control and Experience? Well, it sounds like a pretty good idea, but this task, as Bruno mentioned, isn't an easy one for two main reasons. First, the detection algorithms. Our brain is made up of billions of active neurons, around 170,000 kilometers of combined axon length. When these neurons interact, the chemical reaction emits an electrical impulse which can be measured. The majority of our functional brain is distributed over the outer surface layer of the brain, and to increase the area that's available for mental capacity, the brain's surface is highly folded. Now, this cortical folding presents a significant challenge for interpreting surface electrical impulses. Each individual's cortex is folded differently, very much like a fingerprint. So even though a signal may come from the same functional part of the brain, by the time the structure has been folded, its physical location is very different between individuals, even identical twins. There is no longer any consistency in the surface signals. Our breakthrough was to create an algorithm that unfolds the cortex so that we can map the signals closer to its source and therefore making it capable of working across a mass population. The second challenge is the actual device for observing brainwaves. EEG measurements typically involve a hairnet with an array of sensors, like the one that you can see here in the photo. a technician will put the electrodes onto the scalp using a conductive gel or paste, and usually after a procedure of preparing the scalp by light abrasion. Now, this is quite time-consuming and isn't the most comfortable process. And on top of that, these systems actually cost in the tens of thousands of dollars. So with that, I'd like to invite on stage Evan Grant, who was one of last year's speakers, who's kindly agreed to help me to demonstrate what we've been able to develop. So the device that you see is a 14-channel high-fidelity EEG acquisition system. It doesn't require any scalp preparation, no conductive gel or paste. It only takes a few minutes to put on and for the signals to settle. It's also wireless, so it gives you the freedom to move around. And compared to the tens of thousands of dollars for a traditional EEG system, this headset only costs a few $100s. Now onto the detection algorithms. So facial expressions, as I mentioned before, and emotional experiences are actually designed to work out of the box, with some sensitivity adjustments available for personalization. But with the limited time we have available, I'd like to show you the cognitive suite, which is the ability for you to basically move virtual objects with your mind. Now, Evan is new to this system, so what we have to do first is create a new profile for him. He's obviously not Joanne, so we'll add user, Evan. Okay. So the first thing we need to do with the cognitive suite is to start with training a neutral signal. With neutral, there's nothing in particular that Evan needs to do. He just hangs out, is relaxed. And the idea is to establish a baseline or normal state for his brain, because every brain is different. It takes 8 seconds to do this. And now that that's done, we can choose a movement-based action. So, Evan, choose something that you can visualize clearly in your mind.
Let's do pull.
Okay, so let's choose pull. So the idea here now is that Evan needs to imagine the object coming forward into the screen, and there's a progress bar that will scroll across the screen while he's doing that. The first time, nothing will happen because the system has no idea how he thinks about pull. But maintain that thought for the entire duration of the 8 seconds. So 1, 2, 3, go. Okay, so once we accept this, the cube is live. So let's see if Evan can actually try and imagine pulling. Oh, good job! That's really amazing. So we have a little bit of time available. So I'm going to ask Evan to do a really difficult task. And this one is difficult because it's all about being able to visualize something that doesn't exist in our physical world. This is disappear. So what you want to do, at least with movement-based actions, we do that all the time, so you can visualize it. But with disappear, there's really no analogies. So Evan, what you want to do here is to imagine the cube slowly fading out, okay? Same sort of drill. So 1, 2, 3, go. Okay, let's try that. Oh my goodness, it's just too good. Let's try that again. But we can see that it actually works, even though you can only hold it for a little bit of time. As I said, it's a very difficult process to imagine this. And the great thing about it is that we've only given the software one instance of how he thinks about disappear. As there is a machine learning algorithm in this.
Okay, I think we'll pause there. So the first task was pull. What do you think Evan imagined when he selected pull? Yes, maybe. Sorry? The box getting bigger, so maybe imagining the sensory repercussions of what would happen if the cube was pulled. Maybe, right? He doesn't actually tell us. What else do you think he might have been imagining? Pulling, right? Someone's maybe with both hands, this hand, who knows, right? So the first time, whatever you're imagining, either the box getting bigger or pulling or both, it imagines it. What was Evan imagining when he was asked to make the box disappear? Who knows, right? She mentioned that Evan was a speaker from the TED series last year. Why did she pick a speaker from last year to do this? Part of the reason had to do with this particular hair arrangement. Helps to not have hair. If you go and give a TED talk, right, you're going to be pretty nervous. Hopefully the second time around, not so nervous. Okay, so you have final report 3 due tonight. Final project is all due, and I will see some of you at the CS Fair, and the rest of you I will see during the exam period next week. No quiz due tonight. No quiz tonight.